This is Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss question bank on Module 2, which is quantum mechanics. So, in Module 2 question bank, I am going to start with Part A, which is on analytical questions. So, the first question, numerical problem on Module 2 is calculate the velocity and kinetic energy of an electron having wavelength of 0.21 nanometers. Okay. So, we need to calculate the velocity as well as kinetic energy of electron. So, to start with solution, so first we need to start with given. Whatever is given, we need to write them. So, given is wavelength, lambda is given. So, lambda is 0.21 nanometers. So, you can write it in meters. So, 0.21 into 10 power minus 9 meters. 1 nanometer is 10 power minus 9 meters. So, now we need to calculate velocity. So, we are going to use de Broglie wavelength formula, de Broglie wavelength formula. De Broglie wavelength, lambda is given by h by m into v. Right? So, they have given us lambda and we need to calculate velocity. So, from this equation, I am going to write for velocity, v, velocity, equation for velocity is h by m into lambda. They have mentioned electron. So, we know the mass of electron, right? So, we need to substitute the values. Okay. So, yeah. So, h is Planck's constant 6.626 into 10 power minus 34 divided by mass of electron, that is 9.1 into 10 power minus 31 to lambda is 0.21 into 10 power minus 9. Okay. So, by substituting the values, we will get the velocity as 34.56 into 10 power 5 meters per second. Okay. Once we find out the velocity v, we can find out the calculate. We can calculate the kinetic energy. So, kinetic energy is half m into velocity square. Half mv square is kinetic energy. Okay. So, 1 by 2 m is mass of electron. So, that is 9.1 into 10 power minus 31 into velocity 34.56 into 10 power 5 whole square. Okay. So, the kinetic energy, if you calculate all this, you will get the kinetic energy as 34.182 electron volts. Okay. First, you will get in joules. So, we need to divide the value by 1.6 into 10 power minus 9 because 1 electron volt is 1.6 into 10 power minus 19 joules. Okay. So, once we get the kinetic energy in joules, divide the value by 1.6 into 10 power minus 19 so that you will get the kinetic energy in electron volts. Okay. So, for the given electron having wavelength 0.21 nanometers, we have calculated the velocity. Okay. So, we have calculated the velocity which is 34.56 into 10 power 5 meters per second. And also, we have calculated the kinetic energy which is 34.182 electron volts. Okay. Yeah, so let us go to the next numerical problem. So, basically we have used the de Broglie wavelength equation, lambda is equal to h by m. Let us go to the next problem. So, the next problem is determine the de Broglie wavelength. We need to determine the de Broglie wavelength associated with a proton moving with a velocity of 1 by 10th of velocity of light and mass of proton is given. Okay. So, we need to calculate the wavelength, the de Broglie wavelength for a proton and whose mass is given and it is moving with some velocity which is equal to 1 by 10th of velocity of light. So, we need to know the velocity of light, only then we can take 1 by 10th of that. Okay. So, to start with the solution of this problem, first we need to write with given, whatever is given. So, they have given us the velocity v is 1 by 10 into velocity of light is c. Okay. So, c we should know. So, 3 into 10 power 8 meter per second, we are taking meters. So, 3 into 10 power 8 divided by 10. So, that is v. And mass also they have given, mass of proton is 1.674 into 10 power minus 27 kg. Okay. So, now we need to calculate the de Broglie wavelength. Okay, so de Broglie wavelength formula we have already used in the first numerical problem. De Broglie wavelength is given by lambda is equal to h by m into v. Okay. So yeah, so here they have given velocity and they have also given mass. So we know the Planck's constant. Just substituting the values, we are going to calculate the de Broglie wave. Okay, let us substitute the values. Planck's constant is 6.626 into 10 power minus 34 divided by mass is given as 1.674 into 10 power minus 27 and velocity is 3 into 10 power 8 divided by 10. Okay, so now calculating all these, we will get lambda as 1.31 into 10 power minus 40 meters. Okay, so yeah, that is what we are going to end up. So the de Broglie wavelength of the given proton moving with velocity of 1 by 10th of velocity of light is 1.31 into 10 power minus 40 meters. Okay, so again in this numerical problem also we have used the de Broglie wavelength equation, right? So de Broglie wavelength equation lambda is equal to h by m. And we should know the universal constant velocity of light. Velocity of light is 3 into 10 power 8 meters per second, and we always have to use most of the problem we have to use this Planck's constant. So that is 6.626 into 10 power minus 34 joule second. Okay, so yeah, so these are the universal constant, and we have calculated the de Broglie wavelength for this proton moving with velocity 1 by 10th of velocity of light. Okay, so the de Broglie wavelength found out to be 1.31 into 10 power minus 40 meters. Okay. Yeah, so let us go to the next problem. Okay, so in two of these problems we have used the de Broglie wavelength equation, and yeah. So the next problem is estimate the wavelength of an electron rose to a potential 15 kilovolts. Okay. So we need to estimate the wavelength again of electron which is rose to a potential 15 kV. kV means kilovolts. Okay. Yeah. So to start the solution of this problem, okay, whatever is given, they have given the potential. Potential is given as 15 kV or 15,000 volts. So 15 into 10 power 3 volts. This V is volts. Okay, and we know the de Broglie wavelength for electron that is experiencing some potential. So de Broglie wavelength. Again, de Broglie wavelength. De Broglie wavelength for a charged particle. For a charged particle or for electron. Okay, for a charged particle, let us write for a charged particle with potential V is lambda is equal to h by square root 2m q and v, where q is the charge. Charged particle is having charge q. Okay, so de Broglie wavelength for a charged particle with charge q and potential v is lambda is equal to h by square root 2mqv, where m is mass of the particle, q is charge of the particle, and v is the potential that the particle is experiencing. Okay, so here we know electron mass and electron charge. Okay, so for electron, this is actually for a charged particle, but for an electron, if you substitute the values for electron, electron mass is 9.1 into 10 power minus 31 kg, and charge is 1.6 into 10 power minus 19 coulombs. Okay, by substituting all these values, we will find out that the de Broglie wavelength lambda is actually 12.26 divided by square root V. V is potential angstroms. Okay, so this is the formula, de Broglie wavelength formula for electron. But in general, for any other charged particle, it is lambda is equal to h by square root 2mqv. Okay, so by substituting the potential in this formula, we will get 12.26 by square root 15,000 angstroms. The answer is 0.1 angstroms. So electron experiencing potential of 15 kilovolts, having wavelength 0.1 angstroms. Okay. So here again we have used the de Broglie wavelength formula, but for a charged particle. And by substituting the values of the electron mass and charge in the de Broglie wavelength equation, we have simplified it to lambda is equal to 12.265 square root p angstroms for electron. Okay, so if the problem is based on electron experiencing some potential, you can directly use this formula. Lambda is equal to 12.265 square root p angstroms, where E is the potential. Okay, let us go to the next problem. So the next problem is obtain de Broglie wavelength of neutron. Okay. So now they have given us to find out the de Broglie wavelength of neutron. Where they have given us the neutron kinetic energy is 0.025 electron volts. Okay, so solution, how to find out the de Broglie wavelength of neutron. So first let us start with whatever given. So they have given us the kinetic energy of neutron, which is 0.025 electron volts. They have also given us mass, which is 1.674 into 10 power minus 27 kg. Okay, so there is a direct formula for de Broglie wavelength of de Broglie wavelength, where the input given as kinetic energy. Okay, so de Broglie wavelength. De Broglie wavelength lambda is h by square root 2 me, where this is kinetic energy. We can calculate, we can use this formula directly, or we can calculate the velocity first, and then we can using this kinetic energy formula, half mv square is given as 0.025 electron volts. So from this formula we can calculate velocity because mass is given. So substitute mass and calculate the velocity first. Once we calculate the velocity, then we can calculate this. We can use lambda is equal to h by mv formula, or because they have given directly kinetic energy, so we can substitute this in this formula, right? So lambda is equal to 6.626 into 10 power minus 34 divided by square root 2 into 1.674 into 10 power minus 27 into kinetic energy is given as 0.025 electron volts. You can remove this electron volts also. You can substitute 0.25 into 1.6 into 10 power minus 90. So that whatever you get is in joules. So then the answer is lambda is equal to 0.181 nanometers. This is what you get. So you either use this formula or use this formula. In both of them you will get lambda as 0.181 nanometers. So this is what you are going to find out by substituting. There are two ways of calculating de Broglie wavelength. So this is first one, where you directly use the formula lambda is equal to h by square root 2 me, where E is kinetic energy. Or second way you can solve this problem is first you use this kinetic energy formula. You know the mass of this neutron 1.674 into 10 power minus 27. So substitute m. Then this equation you can write it as, so we want V. So V square is equal to 0.025 into 1.6 into 10 power minus 19 divided by m. Yeah, there will be 2 also. So 2 will come this side. So 2 into, let me write it better. V square is equal to 2 into 0.025 into 1.6 into 10 power minus 19, because it is electron volt. So we are writing 1 electron volt is this, because we want to get it in meters. Yeah, then divided by m. M is 1.674 into 10 power minus 9. So from this equation we will write for V. So then what will V square? This is V square. So if we want V, so V will become the square root of all this. So V will be square root of this. Okay. So we will get velocity, and then we are going to substitute the velocity in this. H is Planck's constant, m is 1.674 into 10 power minus 28. Velocity is evaluated from this equation. So you will get lambda as 0.181 nanometers. So you can, there are two ways. So this is first way and second way. So this is the best way because it is, we are directly substituting the value of kinetic energy. to find out lambda, and that is 0.181 nanometers. Okay, so let us go to the next problem. So the next problem is calculate the velocity and kinetic energy of an electron of wavelength 1.66 into 10 power minus 10 meters. Okay, so again they have asked us to calculate the velocity and kinetic energy of electron with wavelength given as 1.66 into 10 power minus 10 meters. Okay. So we need to calculate the velocity and kinetic energy. So given is the wavelength 1.66 into 10 power minus 10 meters. First we need to calculate velocity. So we are going to use so lambda. So de Broglie wavelength equation we are going to use. So de Broglie wavelength. Lambda is equal to h by m into v. Right? So we want velocity. So velocity will become h by m into lambda. So h is Planck's constant. So 6.626 into 10 power minus 34 divided by m, electron is mentioned. So electron mass we know 9.1 into 10 power minus 31 into lambda is given 1.66 into 10 power minus 10. Okay. So by substituting all these values, we are going to find the velocity first, which is 43.86 into 10 power 5 meters per second. Once we calculate the velocity, then we can calculate kinetic energy. Kinetic energy is defined as half m into v square. Okay, so 1 by 2 into mass of electron 9.1 into 10 power minus 31 into velocity. So 43.86 into 10 power 5 whole square. Okay, so the kinetic energy we will get as 44.7 electrons. Okay, so once you get the energy in joules, you can divide by 1.6 into 10 power minus 19, so that whatever we get is in electron. So the answer is 54.7 electron volts as the kinetic energy, and velocity is 43.86 into 10 power 5 meters per second. Okay. Yeah, so this is the solution of this problem. We'll go to the next problem. An electron is confined in a three-dimensional box of size 0.1 nanometers. Find out the ground state energy and first three excited state energies in electron. Okay, so they're given as electron, and it is confined in a box of size 0.1 nanometers. Okay, so length of the box is mentioned. They have asked us to calculate energies of ground state and first three excited states in electron volts. Okay. So solution, first we have to start with given. So they have given us the length of the box as 0.1 nanometers or 0.1 into 10 power minus 9 meters. So we know the formula for energies of a particle trapped in a box, that is n square h square by 8m ARL. We can take it as L or we can take it as A. A is length of the box. Sometimes people mention it as L. So I am taking it as L. You can take it as A also. No problem. So length of the box is A. Okay. So let me take it as A. Length of the box is A. Okay. So by substituting the values of Planck's constant, mass of electron and length of the box, we can calculate the energy. So they have asked us to calculate ground state energy. So ground state is given by n is equal to 1. N is equal to 1 is the ground state. Okay. So that will be E1. So E1 is n square. So n is 1 square. H square is 6.626 into 10 power minus 34 whole square. So n square h square divided by 8. M is mass of electron 9.1 into 10 power minus 31, and A square. A square is 0.1. I can write it as 10 power minus 10 meters. So 10 power minus 10 meter whole square. Okay. So yeah. So we will get the energy, ground state energy, that is 37.69 electron volts. Okay. So once we get the ground state energy, we can calculate E2, that is the first excited state. So first excited state, that is n is equal to 2. Okay. So n is equal to 2. So we can write E2 as n square into same. This is same, right? So h square by 8 ma square will be for E1, E2, E3, E4, so on and so forth. So only change will be n square. So for n is equal to 2, that will be 4. So 4 into E1 will be the energy of first excited state. Okay. So the energy of first excited state, 4 into E1, E1 is 37.6 into 9. Okay. So energy of the first excited state is 150.7 electron volts. Next, second excited state. Okay, second excited state energy. Second excited state corresponds to n is equal to 3. Okay, so then E3 will be 9 n square. 3 square is 9. 9 into E1. Okay, so E3 will be 339.2 electron volts. Okay, so if you want to calculate the third excited state, for example, third excited state. Third excited state energy, n is equal to 4. That means E4 is 16. 4 square is 16 into E1. Fourth excited state, 4 square. This is third excited. Fourth excited is 5 square. So 25 into E1. So we can calculate the energies. If we calculate the first ground state energy correctly, okay, calculate the ground state energy correctly. First, once you calculate the energy in joules, divide this energy by 1.6 into 10 power minus 19 so that you get it into electron volts. Okay. Once you calculate the ground state energy correctly, then we can calculate other excited states energies just by multiplying n square. First excited n square, that is 2 square. Second excited state n is equal to 3, so that is 3 square is 9, so on and so forth. Okay. Yeah. So first, in this problem, we have used the equation for energies of a particle trapped in a box of side 0.1 nanometers, and for energies of a particle in a box is n square h square by 8 ma square. Okay. So if we know this formula, we can substitute the value of which state you want to calculate, Planck's constant and mass of the particle that is trapped and length of the box. You can calculate different energies. Okay. Okay, so let us move to the next problem. That is seventh problem. Okay. So the seventh problem is calculate the energies that can be possessed by a particle of mass 8.5 into 10 power minus 31 kg, which is placed in an infinite potential box of width 10 power minus 9 meters. Okay, so in this problem, we again need to calculate the energies, that is energies of a particle that is trapped in a box of side 10 power minus 9 meters, and the particle mass is given. Okay, so yeah, so we need to start with the given. So they have given us the mass of the particle 8.5 into 10 power minus 31 kg, and length of the box is given. So length of the box is 10 power minus 9 meters. We need to calculate the energy. So we can calculate the few energies. Okay, let us start with the energies. Okay, energies of a particle in a box. En is equal to n square h square by 8 ma square. Okay. So they have not mentioned what energies we need to calculate. So we are going to calculate few energies. Okay. So first start with ground state. Ground state is the lowest energy state. So that is n is equal to 1. Okay. So then E1 will be n square is 1 square. H square is 6.626 into 10 power minus 34 whole square divided by 8 into electron is, okay, mass is given. So this is not electron but a particle. Okay. So 8.5 into 10 power minus 31 into a square. A square is 10 power minus 9 whole square. Okay. So the energies, ground state energy E1 will be 6.456 into 10 power minus 16 joules. Once you calculate energy, you can calculate the first excited state energy. So first excited state energy. First excited state n is equal to 2. So E2 will be 4 into E1. Okay. So E2 is 4 into E1. E1 is already known. So that is 25.82 into 10 power minus 16 joules. So yeah, we need to know the formula of energies of a particle that is trapped in a box, that is n square h square by 8m a square. If we know this formula, and if we know the Planck's constant and mass of the particle, electron for example, or any other particle, then we can substitute the values and get the energies, different energies, ground state, first excited state, second excited state, so on and so on. Okay, yeah. Let us go to the next problem. Okay, eighth problem is find the lowest energy of an electron confined in a square box of size 0.1 nanometers. Okay. So they have mentioned us, they have asked us to calculate the lowest energy of electron confined in a box of size 0.1 nanometers. Okay. So always start with given is box side A is equal to 0.1 nanometer. So we can convert into meters, 0.1 into 10 power minus 9 meters or 10 power minus 10 meters. Now we know the energies of a particle trapped in a box, n square h square by 8m a square. So they are asking us to calculate the lowest energy state. Lowest energy state is nothing but ground state. Lowest energy state is the ground state, that corresponding to n is equal to 1. Okay, so En is n square h square by 8m square. So E1 is 1 square 6.626 into 10 power minus 34 whole square h square by 8 electron mass 19.1 into 10 power minus 31. A is 10 power minus 10 whole square. Okay, so by substituting 8 m value, mass of the electron 9.1 into 10 power minus 31, and A is given as 0.1 nanometers or 10 power minus 10 meters, because 1 nanometer is 10 power minus 9 meters. Okay, by substituting all the values, we are going to find out E1 as 60.3 into 10 power minus 90 joules. So this is the lowest 60. This is 60. So lowest energy of the electron trapped in the box of size 0.1 nanometers. Okay, yeah. Lowest energy state is nothing but the ground state. N is equal to 1. Okay. So let us go to the next problem, that is ninth problem. Okay, so ninth problem is electrons are accelerated by 344 volts and are reflected from a crystal. The first reflection maximum occurs when glancing angle is 60 degrees. Determine the spacing of the crystal. Okay. So electrons, they are mentioned, accelerated by 344 volts potential from a crystal, and first reflection maximum occurs when angle is 60 degrees. We need to find the spacing of the crystal, D. Okay. Okay. So they have given us voltage potential is 344 volts. This is volts, and they also mentioned the first reflection occurs, so n is equal to 1, and diffraction angle theta also they have given as 60 degrees. We need to calculate the spacing D. So to calculate the spacing D, we need to use Bragg's equation. So Bragg's equation, Bragg's law, we know that 2D sine theta is equal to n into lambda. Okay. So D we need to find out, theta they have given, n also they have given, but lambda they have not given. So we can calculate lambda. Once we calculate lambda, we are going to substitute in this equation. So where we need D, D is equal to n lambda by 2 into sine theta. Okay. So yeah. First, in this equation, we have D is the spacing of the crystal. So spacing of the crystal is D, n lambda by 2 sine theta. N is known, theta is known, but lambda is not known. So lambda is not known, so we can calculate lambda for the electron. So for the electron, lambda is 12.26 by square root V angstroms. Okay. So V is given as 344 volts, so 12.26 by square root 344 angstroms. So we will find out lambda as 0.6 angstroms. Okay, substitute this lambda in this equation. So D is equal to, first lambda is calculated, Then D is equal to N is 1, lambda is 0.6 into angstroms, we can convert into meters, and then 2 sine theta is 60 degrees Celsius. So D will be 0.3 angstroms. So we have calculated the spacing of the crystal, which is turned out to be 0.3 angstroms. To calculate the spacing of the crystal, we had to calculate the wavelength using the formula 12.26 by square root V angstrom. So basically, we have used de Bragg's equation to calculate the spacing of the crystal D. And in order to calculate the spacing of the crystal, we have calculated the de Broglie wavelength of the electron using the formula 12.26 by square root V angstroms, where V is mentioned as 344 volts. Okay. Yeah, so let us go to the next problem. That is the last problem, numerical problem. So the last numerical problem is an electron is bound in one-dimensional infinite potential well of width 10 power minus 10 meters. Find the energy levels in the ground state and first two excited state. Okay. So they have mentioned electron is a particle trapped in potential well of width 10 power minus 10 meters. We need to find out the ground state energy and first two excited state energy. Okay. So now we have done this for so many times that now width A is given as 10 power minus 10 meters, and we need to calculate the ground state. So okay, formula for energies is n square h square by 8 m a square. Okay. So ground state energy, ground state corresponds to n is equal to 1. So E1 will be 1 square into h square 6.626 into 10 power minus 34 whole square divided by 8 m is 9.1 into 10 power minus 31 into A is 10 power minus 10 whole square. Okay, whatever energy we are getting is in joules. Okay, then we have to convert this into electron volts, but here I have just left as it is. So E1 I calculated it as 1.5 into 10 power minus 18 joules. Okay, and the next excited state, yeah, so E1 will come it as 0.376 into 10 power minus 18 joules, and E2 is nothing but 4 into E1, so 4 into E1, so which is 1.5 into 10 power 10 power minus 18 joules, and E3 they have asked us to calculate first two excited states, so E3 will be 9 into E1, so that is 3.38 into 10 power minus 18 joules. Okay. So we have calculated ground state E1 and first excited state and second excited state. Okay. So yeah, so with this I'm going to we have completed all the numerical problems, part A of question bank of module 2, and in the next presentation I will start part B, which is long answer questions on quantum mechanics. Okay. So to summarize, these are some of the textbooks, references books, and to summarize, I basically solved the numerical problems, question bank numerical problems on module 2, and next presentation I will discuss part B of module 2. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.